Okay, so this is 1.4. We're going to be defining the trig functions in this section. We'll be doing some basic computations with them. We'll do applications of the trig functions in 1.5, and we'll do more interesting or more difficult computations in 1.6, which will be next week. All right, so the trig functions, by the trig functions, I mean sines and cosines and tangents, etc. So there'll be three more core trig functions that we'll be talking about, but these three are the main ones. All right, so one thing probably most people have seen here are the sine and cosine and tangent functions, and you've probably seen it defined something like this, right? You have a right triangle, here's your angle theta, this side is the hypotenuse, this side is opposite, this side is adjacent, right? Then probably what you've seen is sine theta is equal to opposite over hypotenuse, cosine theta is equal to adjacent over hypotenuse, tangent theta is equal to opposite over adjacent. All right, and those three, using these opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent as definitions of sines and cosines and tangents, it works in the context of right triangles, like in this picture, but we're going to want to work with trig functions in a far more broad class of situations where you cannot have a triangle, where we still want to work with sines and cosines and tangents, etc. So while these three statements here are certainly true, it's not good enough for us in general, right? And you can kind of see this, right? For example, what is sine of 0 degrees or 0, right? If I were to try to use this definition here, I would have to draw a right triangle, but this angle here would have to be 0 degrees, right? And you can't have that. There is no triangle, right? So according to opposite over hypotenuse, right, sine of 0 doesn't really make sense. In the same way, sine of 90 degrees, right, I would have to draw, just like, again, just following our picture up here, I would have to draw a right angle here. My angle theta would also have to be a right angle, right? So here, the triangle never closes up. And so you can't have, the opposite doesn't even make sense, right? You don't even have a triangle. So again, sine 90 degrees, don't know what it is, right? And of course, anything bigger than 90 degrees, sine 97 degrees, we can't do it, right? In fact, the picture would look like this. We have a right angle, and then we have our theta bigger than 90 degrees. Again, it doesn't close up into a triangle. And so you can't even talk about the words opposite or the word hypotenuse, right? So for any angle that you can't construct a right triangle out of, you can't talk about sines and cosines and tangents of those angles. But that's something we absolutely want to do, especially in the context of circular motion and also periodic motion. For example, a spring bouncing up and down, up and down, up and down, that's modeled by sines and cosines. But working in terms of just triangles like this is too restrictive. All right. So one example here would be if I had a circle, angle like that, that's that big, right? I'm talking about, let's say, circular motion where something is moving in a circle like this, right? I'm very frequently going to want to talk about sines and cosines of this angle, but certainly, again, you can't have a right triangle, right? You can't construct a right triangle out of this because, well, this angle is already bigger than 90 degrees. You've got a right angle on the opposite side, which has to be 90 degrees. So everything is already more than 180 degrees, right? And triangles have to have 180 degrees total. So this is one situation where you're not even allowed to talk about sines, cosines, trig, tangents in the old definition that you probably had in the past, right? So that's why we're going to need a new definition of sines and cosines. And our new definition is in the situation where your angle is, nice and simple between 0 and 90 degrees, it's going to be the same definition as the one that you had in the past. But the new definition will be much more flexible. We'll be allowed to talk about sines and cosines of 0 degrees. We'll be allowed to talk about sine of 90 degrees. We'll be allowed to talk about sine of 175 degrees, or any number, sine of negative 14 degrees, right? So here in your old definition, you can't even start to consider sine of negative 14 degrees because you can't draw a triangle that has an angle of negative 14 degrees, okay? So that's how powerful our new definition is going to be. Okay, so what is our new definition? Well, let's start with a angle like this in standard position. Let me draw a circle like this. All right, let me say this circle is radius 1. Again, circle of radius 1 is the most natural, right? Just a simple radius 1 as opposed to, a circle of radius 27, not as natural as a circle of radius 1, right? So the way we define sine and cosine more mathematically is we look at that point right there. That's a very interesting point because it's where this circle intersects the terminal side of our angle. And one thing we're frequently going to want to know is, if you've, let's say, for example, traveled in circular motion, an angle of theta, right, from the horizontal, one question we might ask is, so you started here, you traveled all the way to there in a circular motion. One question you might want to ask is, well, if we've traveled an angle of theta, what's our new position right there, right? So that guy right there, let me do it like this. This point right there, what are its coordinates? Let me call it question mark and double question mark. Okay. So again, it's a very natural question, right? If you say you've moved an angle of theta in circular motion, right, in a circular motion, what is your current position now? That's essentially what we're asking when we ask what is question mark and double question mark. All right. Okay, so first of all, question mark is the x coordinate of our position, right? Where's that? It's going to be that number right there, okay? The x coordinate. Double question mark, so let me label that. That's question mark. Double question mark is going to be the y coordinate of our position, all right? So here's where sines and cosines comes in. So the definition of sine and cosine, so the definition of cosine of this angle theta right here, is cosine of theta is equal to exactly that x coordinate, all right? Equals x coordinate. All right. The definition of sine is sine of theta is equal to double question mark, which is the y coordinate. All right. So this is really nice because it's a very, very simple definition, number one. Number two, it's these functions now correspond, cosine and sine correspond to geometric objects that make a lot of sense that we would want to consider them, right? It's the position, our position after we've rotated by an amount theta, okay? So in short, this guy right there is cosine theta, comma, sine theta. All right, that's the definition of cosine and sine. All right. Okay, so just as a very, very simple example, if I talk about moving 90 degrees like that, right? That's my theta. Then what is cosine of 90 degrees? What is sine of 90 degrees? Right? So again, if we used our old definition, opposite over hypotenuse, adjacent over hypotenuse, for sine and cosine, we wouldn't be able to define these two things. We wouldn't be able to write down these two things because there is no triangle that can be constructed. But now our new simple definition, everything makes sense. Cosine 90 degrees would be the x-coordinate of that point right there. All right. Sine of 90 degrees would be the y-coordinate of that point right there. Okay. And again, we're talking about a circle here of radius 1. Okay, so what is cosine of 90 degrees? Well, the x-coordinate of that point right there is 0, right? Because this thing is on the y-axis, right? So this is 0. Sine of 90 degrees, well, we're on a circle of radius 1. We're on the y-axis like that. So sine of 90 degrees is 1. So this new definition immediately allows me to talk about sine and cosine of 90 degrees where before we couldn't, right? In exactly the same way, I can talk about if I have theta equals 0 degrees, right? Again, I couldn't draw a triangle, wouldn't even make sense, but cosine of 0 degrees, sine of 0 degrees make perfect sense in my new definition, right? Cosine 0 degrees is the x-coordinate of this point right there. And again, circle of radius 1, all right? The x-coordinate, well, that's just going to be 1. The y-coordinate, this thing is on the x-axis, so the y-coordinate is 0. Okay, and let me emphasize the kind of geometric aspect here, right? So this guy here is at 1, 0, right? This guy here is at 0, 1. And so again, this is equal to cosine of 90 degrees, comma sine of 90 degrees, right? And this guy here is equal to cosine of 0 degrees, oops, comma sine of 0 degrees, all right? Okay, so these are two examples that we said we couldn't do in our earlier definition or our past definition of sines and cosines. But we can do more, like we said. If you have an angle here that's bigger than 90 degrees, again, we said you could not draw a triangle, right, with this theta, or you cannot draw a right triangle with this theta as one of its angles. Okay, so you cannot use the opposite over hypotenuse definition. However, again, we can do it with our new definition, because this point right there, it does have an x-coordinate, it does have a y-coordinate, and so the sines and cosines make perfect sense, right? You just have to measure exactly what this length is here and what this height is here. Okay. All right, notice one thing here that's kind of interesting. This guy here, let me first write the coordinates here are cosine of theta, comma sine of theta, right? Notice that this guy here is negative, right? Because it's on the left side of the y-axis, so numbers on this side here are negative, numbers on that side there are positive, right? So in this situation, cosine is actually a negative number. And sine, well, sine is positive because we're on the positive y-axis, right? But this is something you don't see in the triangle situation. You never had any of the sines and cosines or any of the trig functions be negative numbers. But here, it's definitely allowed, right? In fact, if you draw a general picture here, any angle in the first quadrant is going to have positive sine and cosine, right? Because, well, in the first quadrant, every point, the coordinates are all positive, comma positive, all right? In the, let me write positive, positive, all right? In the second coordinate, quadrant, any point here is going to have its x-coordinate be negative, and its y-coordinate is going to be positive. So here, my cosine, comma sine, right, of my angle, and in this case, we're talking about that angle there, is going to be negative and positive, comma positive. Right? And in exactly the same way, if I talk about an angle down here in the third quadrant, so this would be the angle that goes all the way around to there, right? So this is a really big angle, greater than 180 degrees. My cosine and sine are going to be, well, my cosine is negative, and my x-coordinate is negative, right? And my y-coordinate is also negative. I'm below the x-axis. So this is going to be negative, comma, negative. Okay. And finally, in the fourth quadrant, we can see that if our angle is all the way around like this, right, then we're going to have a positive x-coordinate, but a negative y-coordinate. All right. And so our cosine is going to be positive, sine is going to be negative. All right. I guess I should write it for all of these. This is cosine theta, comma sine theta, right? This is cosine theta, comma sine theta. Okay. So naturally, from our definition of sine and cosines, we can have sine and cosines be 0. We can have them be positive or negative. All right, like I said, this is hugely important because if I were to talk about, an application with circular motion, right, it does make sense that at some point in my circular motion, I've moved around that much, right? And a natural question would be, if I've moved around that much, what is my position, right? And the question of what is my position is the same as asking what is cosine of theta, what is sine of theta, just directly from the definition of cosine and sine. All right. Okay, so one thing to emphasize really heavily here is that our definition, in our definition that we just gave, our circle here is always of radius 1, right? If we do a circle of radius which is not 1, then the x-coordinate is not going to be the cosine. The y-coordinate is not going to be the sine. So one question we can ask is, what happens if we're talking about circles, if I draw the same picture with theta like this, but what if, for whatever reason, I'm interested in a radius that's not 1, let me call it r, right? Then how does this coordinate there, or the coordinate of that point there, relate to cosine and sine? Okay, again, if r is not 1, the coordinates is not going to be cosine theta, sine theta. All right, so the question is, what is it going to be? Well, luckily for us, we know about similar triangles. So if we have a picture like this, let's pretend r is bigger than 1. Then if we kind of mark off a point there where this guy is exactly 1, then we have a triangle like that, a right triangle like that. We have another right triangle like this. These two triangles, so this shaded there, right, and this triangle shaded there, those are similar triangles. Okay, they're both right triangles, right? They share these two sides here. All right. So what that means is that the ratio of their lengths are going to be consistent. So for example, this length right there is cosine theta, right? That length right there is sine theta, right? Because we're talking about radius 1 right there. We're talking about a length 1 right there. And so what is this guy here? Well, the entire length from here to here of the hypotenuse of the bigger triangle is r, right? Because we're talking about a circle of radius r. And so we know that this coordinate here, let me call it x and y, x comma y, all right? We want x and y, okay? So what is x and y? Well, because we have similar triangles, we know that x over r, right, the ratio of this length on the big triangle and the hypotenuse of the big triangle should be equal to the horizontal length of the small triangle, which is cosine theta, over the hypotenuse of the small triangle, which is 1. All right. In the same way, y over r, this ratio, which is the ratio of this height in the big triangle, right, over the hypotenuse of the big triangle, should be equal to sine of theta, the height of the small triangle, over the hypotenuse of the small triangle. So sine theta over 1. Okay. And so immediately, what I see is x is equal to r cos theta, and I see y is equal to r sine theta. Okay, so the situation where you have a circle of radius which is not 1 is actually not much more complicated. The x and y coordinates are actually just r cos theta and r sine theta. All right, and again, you can see this is consistent in that when r is 1, we just get cos theta comma sine theta, as we expect. All right, that's an equal sign there. Okay, let me draw the picture again just because it's gotten a little messy. So if we do have a circle of radius r here, then the coordinates of that point is r cos theta comma r sine theta. Okay. One way you can actually look at this is to say that cosine theta, let me actually come up to here. If we look at this guy here, this guy actually says that cosine theta equals x over r, and this guy here says sine theta is equal to y over r. So an alternate definition we could have given for sines and cosines is that cosine is the x coordinate, right, from here to here, divided by how far we are from the origin. All right. And what is sine of theta? It's the length from here to here, right? This height of where we are, right? Divided by how far we are from the origin. Okay. So an alternate definition of sine and cosine would be in terms of ratios of your x-coordinate over how far you are from the origin, sine of theta, ratio of your y-coordinate over how far you are from the origin. Okay, and in different contexts, sometimes we'll be using our original definition here. Sometimes we'll be using this expression here, these expressions here. Or, of course, it's the same as these expressions here. Okay, because this guy here is x and this guy here is y. And sometimes we'll be using the original sine is opposite over hypotenuse and so on, because at this point we can see that that definition corresponds to the definition that we just gave, right? If I do have a right triangle like this, here's my theta. Let me draw the axis like this, right? What did we say in the past, right? When you learned sine and cosine, sine was opposite over hypotenuse, which is this over that, right? What is our new definition? According to this, using this ratio idea here, right? That's going to be your y-coordinate over the distance to the origin, right? But we can see in this picture, what is our distance to the origin? It's literally h, right? We can see in this picture, what is y? Our y-coordinate is exactly that height right there, which is O, right? So our old definition, opposite over hypotenuse, is the same as our new definition, opposite over hypotenuse, when we have a nice simple triangle setup, as you probably had in the past. Okay. What about cosine? Same idea. Cosine theta in the past was adjacent over hypotenuse, right? Adjacent would be this side right there, right? Our new definition says cosine theta should be the ratio of our x-coordinate over our distance to the origin. But again, in this picture right here, we can see our distance to the origin is exactly h, and our x-coordinate is exactly a. All right, so our two definitions correspond, are the same in the setting of a simple triangle. So you can still continue to use sine of theta is opposite over hypotenuse, cosine theta is adjacent over hypotenuse when you do have the setup of a triangle. All right. Okay, so a good exercise right now, just to make sure you understand our new definition of sine and cosine, is to figure out what is cosine of pi, what is sine of pi. All right. Another problem, what is cosine of 3 pi over 2? What is sine of 3 pi over 2? And this time we're working with radians. So I'm shifting to radians now as much as possible. Okay. Let's talk about sine and cosine of an angle we'll be working with quite a lot, and that's cosine of pi over 4 and sine of pi over 4. So remember, pi over 4 is 45 degrees. So this is, we're asking what's cosine of 45 degrees, what's sine of 45 degrees. Okay. All right, so let's use our new definition of sine and cosine. And the deal is, probably in the past, you were asked to memorize what these quantities are, right? You probably had to memorize this guy, whatever number this is, whatever number this is, and perhaps they never told you why those numbers were exactly, why those numbers were those numbers. But here we're going to figure it out, all right? So what happens is, if we have this setup here, 45 degrees or pi over 4 angle, pi over 4 like this, we know that we have an isosceles triangle. And let me use our kind of extended definition of sine and cosine, where the coordinates here is r cos theta, r sine theta. All right. I want to do this because I want to draw a very simple triangle, right? So the most simple triangle here is perhaps where this side is 1, this side is 1. Okay. So what is the radius of that? Well, we have 1 squared. So this is a right triangle, of course. 1 squared plus 1 squared. Square root of that should be this hypotenuse, right? So this guy should be square root 1 squared plus 1 squared, so square root 2. Okay. All right. So this tells me my r in this picture here is root 2. That r right there is also root 2. So r is equal to root 2, right? But I also know that r cosine theta, this is the x-coordinate of this point right there, right? What is the x-coordinate of this point right there? It's 1, right? Our sine theta is the y-coordinate of this point, of the same point. What is the y-coordinate? Well, the way I've drawn this picture, the y-coordinate is also 1, right? So I know also that r cos theta, r cos theta is equal to 1, and r sine theta is equal to 1, right? Well, r is root 2, so I'm going to substitute that into here. So root 2 cos theta is equal to 1. Root 2 sine theta is equal to 1. And so cos theta is equal to 1 over root 2, which you can simplify as root 2 over 2. And sine theta is equal to 1, same number, root 2 over 2. Okay. Actually, all my thetas are the same, are pi over 4, right? Maybe I go back and change them all to pi over 4, because we're specifically working with just this angle here, pi over 4. Okay. 45 degrees. All right. Now we're going to be doing a lot of computations in this class, and we're going to be doing a lot of examples. And in order to not have to use a calculator all the time, and in order to have kind of examples which are kind of nice and clean, we're going to ask you to memorize a few values of sine and cosine that is probably not going to be that accessible for you to figure out yourself. And this is mostly just so that we can talk about examples kind of with clean numbers. All right. So this table I'm going to draw right now is something that you're going to have to memorize. If you sit down and try really hard, you probably could figure out exactly why these numbers are what they are. But we're not going to go through it at the moment right now. All right, so the angles I'm specifically talking about are 30 degrees, which is pi over 6 radians. 45 degrees, we actually just talked about this one, but the table goes really well together with the 3 numbers that I'm going to write down, and we'll see why in a second. 60 degrees, which is pi over 3. All right. There certainly are other values of sine and cosine that you should know, but these are ones which, especially the 30 degrees and 60 degrees, are ones which are harder for you to figure out yourself. So it's something that probably is a good idea just to memorize. Okay, so some other ones that you should know or you should be able to figure out easily are, for example, sine and cosine of pi over 2, 90 degrees, right? And that's straight from the definition, and we talked about it. Also sine and cosine of pi, right, 180 degrees. You should be able to figure that out very, very quickly from our new definition of sine and cosine. Okay. All right, so this table is goes like this. Well, first of all, we just figured these two out, right? Oops, sorry, over 2. Now, it goes like this: 1/2, right, and then root 3 over 2. Okay, so the way to remember sine in terms of these angles, 30, 45, and 60 degrees is this one is root 1 over 2, and then it goes to root 2 over 2, and then it goes to root 3 over 2, as you go from 30 degrees, 45 degrees to 60 degrees. Okay? Cosine is the opposite way. So cosine of 30 degrees is root 3 over 2, and then it's root 2 over 2, and then it's root 1 over 2. Okay? So if you remember it like that, it's a lot easier to memorize these guys. And again, if you want to, if you play around with a little bit of triangles and stuff like that, you could figure out exactly why sine of 30 degrees should be 1/2, but we're not going to go through it. Okay, so this table you're going to have to know. For homework problems, for exams, you're going to have to memorize these values. All right. Okay, so one of the things we haven't talked about, so earlier on we talked about sine, cosine, in the past you talked about sine, cosine, tangents. We haven't talked about tangent, right? So what is tangent? Well, the correct way to think of tangent is that tangent of theta is equal to sine theta over cos theta. Okay, so tangent theta is the definition of tangent theta, right? Not the opposite over adjacent that you worked with in the past. And again, this definition is better because it allows me to work with tangent of 297 degrees or tangent of minus 13 degrees. All right. Whereas before with the triangles, you have to be able to draw a triangle to do it. Oh, by the way, what would be, for example, a cosine of minus 45 degrees, right? Well, you draw the picture, minus 45 degrees as you go down this way. Your point is here. So again, it's very straightforward once you've drawn the picture. So cosine of minus 45 degrees would be this length right there, where this length here is 1, right? If I have that as a unit circle. Okay, so it makes perfect sense to talk about cosine of a negative angle, because as long as I can draw this kind of picture with the terminal and the initial sides, then I can talk about sine and cosine, because I can talk about the position, the coordinates of that point right there. Okay, and you might think, why would I care about cosine of minus 45 degrees when it's, it looks like this angle is the same as going around this way, right? But when you talk about motion going clockwise, then you naturally would be talking about cosine of negative 45 degrees, all right? Because you're moving clockwise, so you're moving that direction, okay? All right, in any case, tangent theta is sine theta over cosine theta, all right? So what that means is if you know sine and cosine, then you automatically know tangent, all right? So perhaps in the past, you were asked to also memorize as, I think a lot of people probably were asked to memorize this table up here. If you've seen sine and cosines and tangents before, but probably in the past you also had an entry for tangent, right? But I didn't put an entry for tangent because you don't need it. Because as long as you know the entry for sine and cosine, you can calculate the entry for tangent because you know tangent is sine over cosine. All right. So for example, here, knowing sine of pi over 6 is 1/2, and knowing cosine of pi over 6 is root 3 over 2, I know tangent of pi over 6 is 1/2 over root 3 over 2. All right. And if I simplify that, that's equal to 1 over root 3. So kind of run out of space here. I'm just going to erase this. So this is going to be 1 over root 3, which is the same as root 3 over 3. Okay. All right. Also, for this for pi over 4, what is tangent of pi over 4? It's sine over cosine. So root 2 over 2 over root 2 over 2, which is just going to be 1. Right. What is tangent of pi over 3, 60 degrees? It's going to be root 3 over 2 over 1/2. And if you simplify that, that's just going to be root 3. Right. And again, in the past, maybe you had to memorize that, but I would say don't even bother memorizing it, right? Hopefully we'll be doing enough computations with it that it'll automatically commit to memory, but I would recommend not sitting down and trying to memorize it. Instead, always remember tangent is sine over cosine, all right? And this is how we're gonna work with tangents a lot in our class, just thinking of it as sine over cosine, as opposed to some separate entity of its own. And if you are gonna go on to calculus, that's the correct way also to work with cosine, to work with tangents. Okay, but again, we did, in the past, you said that tangent of theta was opposite over adjacent, right? Does that fit with our new definition of sine over cosine? Well, even in the old definition of tangent as opposite over adjacent, it worked already, right? Because if I fill in this h here, what was sine of theta? It was opposite over hypotenuse. Cosine of theta was adjacent over hypotenuse. And even in the past, right, when you saw this before, sine over cosine was opposite over hypotenuse over adjacent over hypotenuse. The two hypotenuses cancel, so you get opposite over adjacent. Okay, so even in the old definition, you can clearly see that tangent is sine over cosine. All right. All right, so one thing we see here is that it's sine and cosines, which are the most natural trig function entities. Tangent is less natural, but it's still something we work with a lot, because if you look at it like this, right? Tangent is sine over cosine. That means tangent of theta is essentially the x-coordinate, I'm going to put this in quotes, over the y-coordinate, because the x-coordinate is r cos theta, and the y-coordinate is r sine theta. If we're talking about a general sized circle, right? And this x over y, the ratio between the x-coordinate and the y-coordinate, will show up quite a bit in our class, especially later on when we talk about polar coordinates. All right. So while tangent is not as natural as sine and cosine, it is something that does come up pretty naturally. Okay. So we'll talk about computing some of the more difficult sine and cosines and tangents of angles in 1.6. So this section is mostly just focused on giving the definition of sines and cosines. But I mentioned more trig functions, right? So in fact, there's a few more trig functions that that show up from time to time. Very, very much less important in a way than our three core ones, but still you should know them. So another one is secant of theta, cosecant of theta, so that would be this symbol here, CSC, and then cotangent of theta. All right, so this is secant theta, this is cosecant. Usually there's no hyphen there. Cosecant theta, and this one is cotangent theta. All right. Okay. These guys will show up, for example, in calculus because they're related to manipulations that you have to do with sines, cosines, and tangents. Okay. How do we define them? Well, luckily for us, they're defined directly from the sines and cosines. All right, so secant theta, oops, is 1 over cosine theta. That's it. All right, cosecant theta is 1 over sine theta. And now you can probably guess cotangent theta is 1 over tangent theta. Right? So these other three guys are just 1 over each of the core three trig functions. All right, and one way people probably memorize this is which one does secant go with? It goes with the cosine, right? Which one does the cosecant go with? It goes with the it goes with the sine, right? So each one goes with a, there's in each pair here there's one co, right? Secant, cosine, cosecant, sine, cotangent, tangent. All right, so you know, for example, that secant theta is not 1 over sine theta because there's no co in that expression. All right? That's purely a way to memorize it. There's no math content in that. All right. Okay, we won't be working with these three functions very much in our class, but again, in the future, especially if you're going to be doing calculus, you will absolutely be working especially with the secant function. All right, for the final bit of this section, let's talk about solving triangles, solving right triangles. So this is subsection, we have a right triangle. So always a right triangle in this section. We have a certain amount of information about our right triangle. So I know it's a right triangle. I know, let's say, for example, this side is 2. I know this angle, let's say, is pi over 6 radians. All right. So the question is, when we use the word solving a triangle, what we mean is essentially tell me all the other sides and angles. All right. So I've given you this 2 right there, this pi over 6 right there, and this right triangle, this 90 degrees right there, right? Because it's a right triangle. So you have to tell me what this angle is right there, what this length right there is, and what this length right there is, right? So altogether, then we would have all the information, all the side lengths, all the angle sizes. All right. So that's what we mean when we say solving triangles in this class. For now, we're only doing right triangles because we don't have the technology to work with triangles which are not right triangles. But in the later section, we will be spending quite a lot of time solving just general triangles, which do not have to be right triangles. And that'll be a very, very interesting section. Okay, the reason why we can solve right triangles, the reason why this word here is so important is because for a right triangle, we can use the Pythagorean theorem. So Pythagorean theorem can be used, right? And that's the contrast between this situation and the general triangle. You know, if I gave you, let me exaggerate it. So if I draw you a triangle which is not a right triangle, and I told you, you know, this angle here, that side there, and that side there, you know, maybe I said this was 20 degrees, I said this side here was 2, this side here was 4, and I asked you to figure out, you know, what these other angles are, right? I asked you to figure out what this last side is. You would not be able to use the Pythagorean theorem because it's not a right triangle. And so at this moment, there's just no hope of doing it. But in the future, you will be able to do it, okay? All right, but again, we can't do it now because we can use the Pythagorean theorem. All right, so let's give names to the sides we don't know. Let me call this side, well, it is the hypotenuse, right? So let me call this side H. Let me use capital H. Let me call this side here, well, it is next to the pi over 6, so let me call it capital A. All right, and let me call this unknown angle, let me call it theta. All right. Okay. So if we did want to use the Pythagorean theorem, we know that a squared plus 2 squared is equal to h squared. Okay. And what that tells me is that if I figure out a, I have automatically figured out h, and vice versa. If I figure out h, I automatically have figured out a. Because if I know one of them, let's say I figured out a was 7, then I know h squared is 7 squared plus 2 squared, and I've got h immediately, right? So that's the power of the Pythagorean theorem in this situation, all right? Okay, so if I wanted to use the Pythagorean theorem, that's how I would use it, all right? Okay, in any case, I think for this problem, probably the easiest thing is to figure out what theta is first, because we have 2 of the angles, and we know a triangle has to have a total of 180 degrees. 180 degrees is pi radians. So I know that theta, let me do it in theta plus pi over 6 plus 90 degrees, which is pi over 2, has to be 180 degrees, which is pi. All right? And I highly encourage you at this moment to start working with radians as much as possible, just to get comfortable with them. Okay, so this is the same as theta is equal to, let me add these two together. So this is 6, plus is equal to pi, right? 4 pi over 6, I can simplify that. That's, 2 pi over 3 equals pi. And then I just throw that to the other side. I get theta equals pi minus 2 pi over 3, which is pi over 3. Okay. So immediately we have our theta, it's pi over 3. Now for the two sides. Let's see. We know that, actually we can use it, we don't necessarily have to use the Pythagorean theorem here. We could if we wanted to, like I said, but in this situation, we can use our old concepts of sines and cosines, right? We know that, for example, sine of pi over 6 is opposite over hypotenuse, right? So sine, so let me put a check there in that we finished with our theta. Sine of pi over 6 is opposite over hypotenuse, right? Our opposite was 2. Our hypotenuse is the thing that we don't know, right? But we just said sine of pi over 6 was 1/2, okay, from the table that you're supposed to memorize. And so immediately I can solve, let me clean this up. This says 1/2 is equal to 2 over h, right? Which tells me h is equal to 4, okay? So let me update our picture. So now we have right angle there. We know this is pi over 6. We know that's pi over 3. We were told this was 2, and we just figured out that this h was 4. Okay. So at this point, we could use the Pythagorean theorem, right? And if we were to do that, then we would know that using up here, a squared plus 2 squared is equal to h squared, right? A squared plus 2 squared is equal to h squared. H is 4 squared, right? That would tell me a squared is equal to 16 minus 4, which is 12. And so a is equal to plus or minus root 12. But we're talking about an actual triangle here, so it can't be negative root 12, so it has to be positive root 12. Okay? And if I wanted to simplify that, that would be 2 root 3. All right? Okay, so that guy right there is 2 root 3. That's one way to do it if we wanted to use the Pythagorean theorem. But alternatively, we could say cosine of pi over 6. Once we figured out the hypotenuse, we know that cosine pi over 6 is adjacent over hypotenuse, which is adjacent over 4, right? We know cosine of pi over 6 is root 3 over 2 from our table. And so altogether we have root 3 over 2 equals a over 4, which tells me a is equal to, throw the 4 to the other side, 2 root 3. Of course, we get the same answer either way we do it. Okay? So this is what we mean by solving a triangle. So now we have all the sides, all the angles of this particular triangle. All right, and again, the technique is essentially to use the Pythagorean theorem if we want, to use the definitions of the trig functions in terms of actually the old definitions, opposite over adjacent and so on. All right, let me make a comment here about the online homework. So you'll probably see problems in online homework similar to this one here, but the angle they give you, so in this one, I set it up specifically so that, for example, let me scroll all the way up here. For example, this angle right there, I set it up so that that angle right there, we knew the sines and cosines of from the table, right? But in the online homework, you'll see a situation where perhaps almost the same setup. Let's say this was 2, this is a right angle, and this is something that we don't know, right? Let's say 20 degrees, right? Well, we don't know sine, cosine, tangents, anything of 20 degrees. So for those problems, you're just going to have to use a calculator, all right? So how would that work? So for example, this hypotenuse side, we know that sine of 20 degrees, so this is literally the same thing we did just now, except with pi over 6, is equal to opposite over hypotenuse, 2 over h. And so that tells me h is equal to 2 over sine of 20 degrees. All right, and then here you'd have to use a calculator. Okay, there's no other choice because we don't know that number. One thing to note: when you do use a calculator, make sure you know whether your calculator is calculating in degrees or radians, and to switch it if necessary, because it's super frustrating to get the wrong answer because of that. All right, one other situation that you'll be seeing is maybe one where you're given information like this. So let's say this is 4 and this is a 1, right? That's a right angle as usual, and you want to solve the triangle, right? So you need this angle, you need that angle, and you need this side here. Those are the three things you have to figure out. So the question is, how would we figure out, for example, let me call this guy theta. How would we figure out that angle? Well, again, you can just use the definition of, again, the old definition will work, because this is a right triangle. The old definition of cosine is cosine of theta is equal to 1/4 adjacent over hypotenuse. All right? Okay, so if this right-hand side were a number from the table, then we would know theta, right? For example, if this right-hand side were 1/2, right, then theta would be, well, cosine of theta is equal to 1/2. What does theta have to be? From the table, we know theta is pi over 3. Okay? So in those situations, you're expected to actually be able to figure this out without a calculator. All right? However, that's not the situation we're in, right? We have cosine theta equals 1/4. That's not one of the ones we know. So here you're going to have to use a calculator. All right? How do you use a calculator? Well, you use the cosine inverse, and sometimes it's called the, on a calculator, it might be the arc cosine button or function of your calculator, or, you know, whatever calculating device you're using or calculating app you're using. All right? So use these two guys, either of these two buttons on whatever app you're using. And the way you use it is, you know, you press the button arc cosine of 1/4. This is equal to angle. All right. So this arc cosine, or the cosine inverse function or button is let me actually write out theta. Is the thing that goes backwards. All right. It's the thing that so cosine, usually you plug in an angle and you get the x coordinate. Right? Remember, cosine theta is the x coordinate. Arc cosine is where you plug in the x coordinate and output is the angle. All right? So it's the thing that goes backwards. Okay? So let me write it over here. So cosine goes from angle to x coordinate. All right? So arc cosine goes from x coordinate to angle. All right, so it allows us to move backwards. And so using that function of your calculator will get you this theta right here. All right. It's kind of weird how I described it, because we're actually going to go very in depth into these functions here. And they're properly, you know, to be thought of as inverse functions to the cosine function. Same with arc sine, inverse function to the sine function, and arc tangent, which is the inverse function to the tangent function. We're going to go pretty in depth into them. Right now, just think of them as a button on a calculator, which tells you the answer when you're working with triangles. All right, and I add that last point because technically there's huge problems with the concept of arc cosine with this idea of going backwards. There's huge problems with this concept, but in the context of triangles, everything is cool. So just use the button on your calculator and you should be okay. All right. We'll talk about the complications in the future when we get to it. All right. You won't see too many problems in section 1.4. It's mostly a kind of conceptual section, but we will be using all these ideas in the next section. So you'll see a chunk of problems in 1.5 on the homework.